Thanks for inviting me to be here. It's always fun to come home to Tennessee. I'm a professor at Harvard. I'm trying to be a scientist and an engineer up there. And some days I have good days and some days I have bad days. I have a group of scientists, and one of the things that we're very concerned with, there's physicists, engineers, chemists, mathematicians, we have artists. We have a lot of people in the group, and we all look at the science through a different lens. And one of the things we're always debating is what's important. What's important to work on? And when we do this, every time we think that we've come up with an idea of what's going to be important to work on, I go to church, I go to a party, I sit down next to one of you on an airplane, and you ask me what I do, and I explain, hey, I look at how cells and tissues build themselves. And I see the eyes glaze over, and they emotionally and mentally disconnect from me. And I'm not going to say that I don't use this to my advantage when I don't want to talk to you on a plane. But just after you put all this work into trying to understand what an important problem is to work on, you sit down and you explain it to somebody, and it doesn't register. It's not part of their problem. And so we go on back and forth in my research group about what's important. And we have a very diverse group. And I said we have physicists, engineers, chemists, artists, clinicians in training. We also have a bunch of gunslingers. Over the years, veterans of the war in Iraq and Afghanistan, from every branch of the service and from coalition partners have kind of wandered into our laboratory as part of their education, training to work on problems that they brought with them. And I think we found each other because I also have another pursuit besides my gig at Harvard. Every once in a while I have to go over to Afghanistan and do my thing over there. And as time has gone on and we've had more and more veterans come into the lab, we've started to discuss the things that we saw in the wars in Iraq and Afghanistan. And when I first got to Harvard, I didn't want to be the veteran on campus. So I kind of divorced my laboratory from the war, and I focused on trying to understand the heart. But over time, more and more government agencies started calling me, asking me to consult with on various technical problems or scientific problems that were coming up on the battlefield. And it wasn't so much because I'm a great scientist or a great warrior. It's just I was the only scientist they'd ever known that had been shot at, so I got called for that reason. But I remember I kept these worlds very separate for a long time, and then I got a phone call from a buddy of mine who'd been wounded in Ramadi, and he got hit by an IED. And over a series of phone calls, we had this discussion. And I remember one night, very distinctly, a conversation. I was very frustrated. This was 2005, 2006. We still didn't really have a good idea as to how to treat traumatic brain injury, and that's what this guy was suffering from. And when I hung up the phone, I said, hey, I got to get in this. I think I muttered a few expletives before I said that because I wasn't really wanting to do it. But this is going to be on the internet, and my mom cyber patrols for me, and I don't want her to hear me talking soldier language. So we decided to get into it. So this is a video we took in one of my last patrols in 2009, and improvised explosive devices. Hey, can you kill that volume? Can you turn that volume down a little bit? Improvised explosive devices are kind of the weapons of choice in Iraq and Afghanistan. They've been around for a long time, and now we saw them. We had them in Boston, the Boston Marathon bombing. If you're in New York, you knew there was a vehicle-borne improvised explosive device a couple of years ago in Times Square. And what this device has made part of the public discussion is something that we've known for a long time, and that is traumatic brain injury is a pretty nasty disease. Your brain is a mechanically protected organ. It's inside your skull because it's really soft. And when that blast wave propagates away from the explosion, your brain slams up against the inside of your skull, and these neurons, the cells that make up the networks that allow you to sing, to remember loved ones, to speak, to count your change when you go to the Burger King, they get torn, they get compressed, they get twisted, and it breaks up these architectures. And now we know that this kind of mechanics and this kind of injury like you see here, and this is Josh Goss, a Marine in my lab who did 2 tours in Iraq who made this movie. Now we know that once we have this blast, we're potentiating a cascade of events that eventually wind up potentiating diseases like Alzheimer's, Parkinson's, and Lou Gehrig's disease. And the outcomes for the diseases, I mean, I think we all know them, they're very, very cruel diseases. And so now we're on the battlefield after 10 plus years at war. We've got soldiers that are coming back that have been blown up 10, 12 times before they're 30 years of age. So we really have a problem. So as I started taking a look at this problem after I hung up the phone that night, I started thinking about trauma research and why we don't do a lot of it. It's because the experiments are nasty. They're really tough. A lot of times they require animal experiments, and no one enjoys that, even if you do like animal experiments. So I figured, hey, listen, you know, if I start blowing up goats on Harvard Yard, I'm not going to last very long there, so I need to develop some tool sets. So what we did was the veterans in my laboratory combined with the graduate students and the postdocs to combine everything we knew about explosives and IEDs with everything we knew about cell and tissue engineering. And what we decided to do was to recreate the whole energy spectrum of an IED blast on a small piece of brain that we had built by hand and put it onto a chip like you see there, and mimic all the different mechanical injuries that parts of your brain feel when you get a concussion. And whether it's an IED blast or a blindside quarterback who's getting sacked or your head snapping forward when you have a car accident, all these injuries to the brain mean traumatic brain injury. Concussion is traumatic brain injury. And so Matt Hemphill and Josh Goss and Borna DeBerry and my group combined to build all these tools. And what we found once we build these things is we yielded some fundamental new insights as to how to treat traumatic brain injury or what might be the cause of traumatic brain injury. And before, where we thought that the blast wave propagating through the neurons had just kind of ripped open their skin, the membrane on the neurons, we knew now that there was a specialized set of proteins inside these neurons that are activated by this traumatic injury, and that they start signaling cascades that hopefully can be reversed. And what was really important about these insights was that it kind of puts the science back onto the sweet spot of the pharmaceutical and biotech companies, the guys that go out there and develop the cures to the diseases that ail us. So this was a big move for us, the whole idea to develop this tool set and jump into this traumatic brain injury. So the other thing you see on the battlefield is what happens when high velocity projectiles and fire make contact with flesh, and it's not very pretty. And you know, I have many friends who've come back from Iraq and Afghanistan with debilitating scars. And so we started thinking about how we can heal these wounds. So a postdoc in my group, Mohammed Badarasmi, with a background in textiles, and Josh Goss acted on this idea that I had several years before. And it was an idea that I thought was a good idea, but I couldn't get any of my students to work on it because they thought it was too simple. I had this idea that we could use a cotton candy machine to make nanofibers. And the whole idea was I wanted to make nanofibers out of a very specific protein. And this protein is called fibronectin. It turns out that when you do surgery on a baby that's still in the womb, when the baby's born, there's no scar. And the reason there's no scar is because in their skin, there's a lot of this protein called fibronectin. And we had this idea that if we could make wound dressings out of this protein, then what we could do is we could make a nanofiber scaffold so that put it down onto the wound, the cells could kind of walk over the scaffold to close the wound. So I was going back out to Afghanistan. Josh Goss had just gotten back from Iraq. We kind of zigzagged back and forth between the theaters. And I told him, I said, we bought this cotton candy machine, put it in the lab, I said, let people play with it, build this thing, I got to go back to the war. And I came back about 7 months later. There was a pile of broken equipment in one corner of the laboratory, and what they'd done is ripped the engine, or the motor off of a centrifuge and coupled it on that cotton candy machine. And what we found was that we could produce, like the movie's not running there in the center, but we could produce nanofibers. And this was important because fibronectin can't be made into it's kind of like a protein like you've heard of silk. It's a globular protein, and in order to form a fiber, you have to unfold it and make this long, continuous line where they can kind of grasp hands. We had to control the nozzles and make these nozzles so that we could unfold the proteins and induce fibrillogenesis, and we did. And so Holly Galecki and Patrick Campbell in our group started putting these wound dressings down on doing some animal experiments. And what we found was that the wounds closed faster, was less scarring, there was less infection, and they were more likely to see hair follicles. And we really think this is great. We're getting ready to go into human experiments with this. The whole idea is that we can take a girl who looks like this and make her feel as good about herself as we feel about her. So this is the endorsement part of my talk. My name's Kit Parker, and when I'm in a firefight, I like to not get shot. And that's an adaptation of a line from my daughter who was explaining to me how she felt about taking a bath one night. You know you're hurt when you're knocking off your 5-year-old for material to talk about. But so camouflage, and you might be following this in the news because there were stories about this week, camouflage is designed to help you not be seen. And you can see here that on this kind of aqua blue suit that the style managers at the Department of the Army picked for us to wear in Afghanistan, not necessarily blending into the desert there. And this was very controversial. There were congressional hearings about this, and they actually went out after we had this in Afghanistan for a couple of years and developed a camouflage pattern just for Afghanistan because people were getting killed wearing this. I mean, this is a very bad fashion mistake. We operate on the battlefield in a variety of different environments, from the desert to mountain valleys. And every service has, over the last few years, adopted their own camouflage patterns. And what this tells you is two things. You can see the Army one, you can see the Marine one, you can see the Air Force one. The blue one is the Navy, because if you fall off a ship in the ocean, you really want to blend in. But what you notice here is something really important. These services were making a fashion statement with their camouflage. And I would argue that fashion is the inverse problem of camouflage. In camouflage, I don't want to be seen. In fashion, I want to be seen, I want to make a statement. So if you're making a statement with your camouflage pattern, you're not camouflage. And that's the problem we're having right now. So we took a kind of a unique approach in our group. We did two things. First of all, we started taking a look at the cuttlefish. The cuttlefish over here on your left has a unique ability to blend into its local environment by changing these little things in its skin. And we wanted to understand how they do this, how they camouflage themselves so well. And then we started studying the inverse problem. I taught a class on fashion design. And I don't know if we've ever taught fashion design before me at the engineering school at Harvard. It was kind of looked at kind of strange. But the whole idea was to make dresses and to put technologies in these dresses so that we could do adaptive coloration. And the coloration was going to make the garment, the fashion statement, bigger than just the garment. All these colorations had various sensors on it to sense the local environment, the social terrain, the geoterrain, the physiology of the wearer, and change the lighting accordingly. But going back to the cuttlefish, because this is what kind of inspired this thing. I had a postdoc in my group, Layla Daravi, and we teamed up with Evelyn Hugh at Harvard and Roger Hanlon at the Marine Biological Laboratory in Woods Hole, Massachusetts. And we took this cuttlefish and we took its skin apart and we started breaking down these little things. And these, so I don't have a pointer here, but you can see these little dots on its skin. These are little bags of proteins, and these proteins are on this long tethered skin, long protein tether, nanofiber. And it turns out they have these lenses, they have absorbers, they have proteins that emit light. And the cuttlefish has all this packed into thousands of these little bags on its skin, and it modulates the size of these bags relative to whatever the ambient lighting conditions or whatever the foliage, whatever the vegetation is around it, or whatever predator is coming after them. And so what Layla did was break this thing down and try to understand or reverse engineer this nanophotonic architecture inside these bags. And now what we started doing is taking these proteins out, and Layla's been putting them into the nanofibers that come out of the cotton candy machine. The whole idea is to see if we can replicate this ability to camouflage our clothing the same way a cuttlefish does. What we see is that there's no fundamental laws against an invisible suit. The cuttlefish has this. If we can replicate this in clothing, then whether or not you duck hunt or you go to Afghanistan or Iraq, you might have better camouflage. Now, one of the things that has gotten a little bit of attention that we were working on was this counterinsurgency idea. So the wars in Iraq and Afghanistan and other places where we've been over the last few years are all based on counterinsurgency. And counterinsurgency is about one village at a time. It's not about night raids and predator strikes. Counterinsurgency is about me finding a friend and having that friend take me to the enemy. Finding a friend in a village, having them buy into the idea of a civil society, buy into the idea of sending their little girls to school, buy into the idea of rejecting violent extremism. And we as a military are really good at killing people and breaking things. But if you ask me how to get to that picture on the right where I'm making friends, they got nothing for me. It's all about force of personality. There's no doctrinal template for that. It turns out over the years, over the last 100 years, the defense industrial complex has developed all the tools we need to kill people and break things. If a Soviet-era T-72 tank comes into the middle of some field somewhere, I've got computer programs and algorithms, this is all Newtonian physics, that tell me exactly how much ordnance I've got to put down in that tank in order to destroy it. But if I got to go into a village and I don't have any language skills, And this guy is 20, 30 years my senior, and he's been living there for a long time, completely versed in his own culture, and I'm not. There's nothing to make a friend. I mean, the fragrance industry might argue that they can help you make a friend, but that's not going to work with this guy. So the whole idea is, should there be science and technology to support this? How do you make a friend? Now, when I was in Afghanistan on my first tour, that's when we started using money as a weapon system. And if you see there in my pocket there's a wad of $10,000 in cash. Every time I left the wire or went on a patrol, I was armed, had a gun, and I had a wad of cash. And the whole idea was that, you go into a village, and in many ways, you reduce down to either buy them or you kill them. And you know that using money as a weapon system or money to buy friends is not going to be a sustainable model for fighting a war. And there's no, and no one's fooling anybody. The people there in Iraq or Afghanistan, they're not buying into this. But if I hold out a wad of cash and I hold up my gun, which option do you think they're going to take, at least for the time being? So the whole idea of, if this is the primary weapon system we've got, we're really hurting. And so when I came back from being in Afghanistan in 2009, I had heard about this gang problem in Salinas, California, and how the police department there had spoken to some people on counterinsurgency theory, because they were thinking about using it for gangs. And this isn't so far-fetched. Gangs evolve into an insurgency, and when you beat an insurgency, they devolve into a gang. So it's part of the spectrum of conflict. So I went there, and it turned out the conversations hadn't really gone far. So I spent the night going to gang hangouts in Salinas. And I had this idea that we could develop a lab, a counterinsurgency laboratory, where we could test ideas, where we could build technologies. The whole idea of try to understand the science of how I've got to go into a village, make a friend, and help them stand up and defend themselves. Because all these gangs and insurgencies, they operate in the same way. They exploit at-risk populations, whether it's a neighborhood that's impoverished in the U.S., or if it's a country like Sudan or Afghanistan or somewhere in Africa. They exploit at-risk populations. So I went around and started singing this idea of about a counterinsurgency laboratory to various government agencies, and I gave one talk at a defense industry conference where they asked me to be the keynote. It went over like a rock. The whole idea that I wanted to do some science to understand how to make friends, no one could conceive how that was going to work with their current business models. So one weekend I'm at my National Guard unit, and I'm talking to some friends of mine, because they were about the only ones that would listen to me, about the whole idea of developing a counterinsurgency laboratory and using inner-city gangs as a model for these insurgents. And across the table from me in the conference room was an Army buddy of mine named Mike Cottone. And Mike Cottone is a 20-year-plus Special Forces veteran, and he's also a Massachusetts State Trooper. He said, "Hey, Kit, listen, we're starting to do this." He had come back from a tour in Iraq to the north end of Springfield, Mass. And what he'd found was gangs with gangbangers riding down the street on motorcycles with assault rifles over their back. I mean, just a completely out-of-control neighborhood. And so he got permission to start applying counterinsurgency techniques there. And this was about the same time I was having this idea, although we weren't, talking to each other about it until that weekend at National Guard, about a counterinsurgency laboratory. So it turned out another Army buddy, Tom Saroof, and a group of military veterans, about 4 or 5 of them in the Massachusetts State Police, had been given permission to kind of go rogue and operate inside this neighborhood in the north end of Springfield. And so I went down there and I started talking to them about this thing, and I realized right away, hey, they needed some tools and they needed some metrics. They needed someone to apply some analytics. If you saw the movie Moneyball, when you start applying quantitative analytics to baseball players, they need some quantitative analytics to be applied to what they were doing. It didn't necessarily boil down to how many people you arrested or how many people you convicted. It meant everything from standardized test scores to sexually transmitted disease rates to litter and graffiti and all the other things that seem to be spiking or going down in a neighborhood that's got a really bad gang problem. So after I realized that we had no funding for this, and so I went to the dean and I said, hey, I want to teach this class on how to apply it's an engineering design class, and I want to teach how to apply counterinsurgency theory against gangs. The town's 2 hours away from Boston. It's got a whole bunch of crack houses and heroin dealers in there. I'm going to take the students down there a couple days a week. It's going to be cool. And the dean said, okay. I got fantastic support from Harvard from this. So born at DeBerry, the same guy who'd helped me kind of beat back the paradigm in traumatic brain injury volunteered to be the teaching fellow for this. And we started this. We took a room inside a building in engineering school, and we set up basically an intelligence cell. We blacked out the windows, and we put maps up where we had every crack house mapped out there in the north end of Springfield. And we got to work. One group of students, we had 12 students take the class. One group of students started working on developing analytics. We were out there on the streets with the state troopers. We'd go door to door on non-kinetic operations. We were just spreading the word about services. We had students in patrol cars. We had students in helicopters patrolling around there. We were there probably putting about 250 man-hours a week into this neighborhood between myself and my students. And that's quite a bit for one class. We also had another group that started designing software, social network analysis software, because you didn't just want an arrest. You wanted the right arrest. A lot of these kids were in situations where joining the gang was almost like the only option they thought they had. They didn't know where one of their parents was. They didn't know where their next meal was coming from. They were getting beat up on their way to school. The first time I'd gone down to this neighborhood, Mike had me come down there when they were having this community leaders meeting. They called it a community elders meeting. And I walked in, and it was just like the village elder meetings I used to run 2 or 3 times a day on my first tour in Afghanistan, going through one kid at a time. Hey, this kid's at risk. Mama doesn't have a job. Daddy's away. We need to find something for him to do after school. And remember, this is after 2008, 2009. So the funding coming into the city for after-school programs to keep these kids from 14 to 18 years of age, what the gangs call the posses. And they like to use them because they don't hit the mandatory sentencing laws until they're about 18. There was nothing for these kids to do. So you enlisted the local law enforcement leaders, and the whole idea was not for them to call the police so the police could go in there and kick a door. The whole idea was to empower the community and let them feel like, hey, the police is my instrument to help me clean up my own neighborhood. So the students did all this fantastic work. It was got quite a bit of press. The students who did this software spun out a company called Mark 43, a fantastic story. They're selling their software to gang task force and police departments across the country right now. The analytics are being applied for. It's gone all the way up to the national security staff, and police chiefs from around the country and around the world have been contacted us asking what to do because gang membership's exploding. So the point is we felt like we were hitting all parts of the war. For every buddy of mine downrange that was facing something, whether it was a village that he was trying to like help them, lead them to like a different outcome, or someone facing some debilitating wounds of war, we were trying to do a little bit of everything to help them. So if you go back to my original question, what's important science? So as we started doing this, it really kind of changed my life. It changed my career because, you know, at least a half, maybe almost 2/3 of the portfolio in my research group now are projects that we brought back from the battlefield. And we've got more on body armor and a variety of different things that we're working on. And these young veterans have come off the battlefield, and they're very motivated to use all their subject matter expertise as they go on. Some of them are community college students, some are 4-year schools there in Boston area, and some of them come around from the country. And it dawned on me that if you ask the question, what's the important science? It's not so much what's the important science, it's what's the important anything that you do. And the most important thing that you work on is a thing that affects the lives of the people that you love the most. Thank you.